Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello, my name is Dan Goldman, and my group mainly works on problems involving movement of animals and physical models of animals, which look like robots. And we also like to try to understand some of the interactions, environmental interactions that those animals, what we call terradynamic environments.
Yeah, great. So I'm curious about the embodied intelligence case. How do you see this concept when it comes to design, the robot you design? Is it, you believe it should be in the patient's brain side and the body side of morphology, or just morphology itself? So how do you see this concept here?
Well, it's an interesting concept. I'm not fully sure I understand what we mean when we say embodied intelligence. Maybe you can, in fact, enlighten me a little bit. I have an idea of what it could be, but maybe you could give me some of your definitions.
Yeah, it's interesting. Actually, based on the interviews, there is no specific definition, but I believe that's very interesting when it comes to robotics, the intelligence through the body itself, not the brain side. And I think that's something is very interesting, that we shouldn't always focus on the brain side, for example, or maybe both, but I believe sometimes it could be interesting through the body itself. So I'm curious, what do you think?
Yeah. I agree completely. My belief in this philosophy, or entree into this philosophy, actually started when I was a postdoc. So I was a PhD student in physics, and I studied nonlinear dynamics, which started back in the 60s and 70s with people investigating how systems with few degrees of freedom, and don't worry, I'm going somewhere, so I'm getting to it, how systems with few degrees of freedom could display remarkably complex behavior. In fact, this goes back all the way to Henri Poincaré, who was interested in studying the so-called three-body problem in physics. If I have two orbiting bodies under Newton gravitation, I can essentially solve that dynamical system analytically and predict the motion of the planets or the stars or whatever you like forever and ever and ever. But as soon as I add a third body into the mix, can't solve it analytically anymore. And in fact, the dynamics in such a system are remarkably complex. So complex that in fact it took, 50, 60, 70 more years beyond Poincaré for people to start to get a hint of such complexity once they were able to start to solve those equations on the computer. And so my background and my baseline assumes that any physical system with more than 2 degrees of freedom is going to be potentially remarkably complex. So complex that it's very hard to predict how to control it a priori, how to design it, et cetera, et cetera. That's just sort of a baseline philosophy. So when it comes to an organism, right, the idea that or a robot for that matter, the idea that we can understand its interaction with complex environments or even relatively simple environments without understanding something about the mechanics, to me, is almost laughable. So that's my philosophy. I didn't answer your question exactly, but I'm telling you what I believe is that the odds of making robots, which are only essentially brains in a jar, robotic brains in a jar connected to legs or bodies, and have them succeed in real world environments I think is a philosophy doomed to. So I think that in fact the body and the mechanics, and I mean that across scales, and I have an example from our own lab of where we're trying to make progress on that, on the seemingly lowly little nematode worm C. elegans. The mechanics across scales is absolutely critical to understand how a little nematode worm can move around in environments more complex than anything our best robots Yes. And indeed, some of that is through its nervous system, but much of that is through the body properties, its muscle properties, what have you. So that's my kind of long-winded story of why I believe in that mechanics and what we'll call active mechanics are so important to understand. So,
Interesting, yeah. So I'm curious, in that case, when we apply what you mentioned in soft robotics, for example, what do you think maybe could be missing in understanding? For example, when we see the dead fish swimming upstream and still, can have kind of, I don't know, its morphology or properties of the environment as well. So how do you see this kind of conscious experience that still functions with the body itself without having the brain? What could be missing in understanding here?
oh, well, what isn't missing, I guess, is my question, right? I think we are very, well, okay. Let me go back to my multi-degree of freedom system. Any system which has sufficient number of degrees of freedom, but not too many degrees of freedom where I can continuum, but not too few where it's all very simple, I think can have interesting and surprising dynamics, which can sometimes be mitigated by control, but sometimes can provide challenges for and surprises. So indeed, a dead fish that can seemingly swim upstream because of novel mechanics, fluid mechanics, elasto-hydrodynamic coupling. That's a great question. And I don't know the state of the literature on that, but I would be impressed if people have a deep understanding of the mechanics that allows such such swimming to take place.
Yeah.
I'd be impressed. So if we don't understand that, using your example, how can we credibly say we can, design in a rational way, in a systematic way? Now we may be able to come up with cool, build cool things and then test them out, but we may not have an understanding of why they work, a deep understanding of why they work.
Great.
I would bet that that's the rule, not the exception, for most of soft robots interacting with real environments at this stage, which is kind of interesting to think how in the 21st century, right? I can't predict why a kind of soft robotic worm succeeds in certain environments and fails in others.
Great. So I guess if there's something through your work also, because you have been studying, for example, lizard, and is there any counterintuitive, something doesn't make sense to you, and when you try to deploy it was counterintuitive or surprising how it behaves in such behavior? I don't know if you have something like that.
Yeah, well, in fact, I can tell you that one, I'm not sure about there's plenty of things that we find that are counterintuitive that, I, as an experimental physicist, I tend to go into studying a system expecting surprises and expecting new phenomena. So we take a robot. One of my favorite examples is you take a robot which looks like a snake or an worm, which is a bunch of serially connected motors which are oscillating sinusoidally and phased appropriately. So a traveling wave of body, of motor bending goes from head to tail. You put wheels on the belly of that robot and you put it on a smooth, flat surface. And if you set parameters correctly, then the robot looks like it sort of swim the environment, kind of do a lateral undulation. By the way, lateral undulation, which is so seemingly beautiful and simple, is very hard for limbless robots to achieve. That's just an interesting point. But anyway, you achieve it in limbless robots. You kind of fake it by putting wheels on the belly, and that generates a so-called drag anisotropy of the right kind to propel it forward. Then you interpose obstacles in the way, and you don't put any sensors on the robot. No sensing, no contact sensing, no vision, no nothing. You just let the robot play its wave and control or keep the wave on the body to the best it can, and the motors we use, it do a good job. And you let it collide with various obstacles. And one thing that emerges is that if you do that you make an array of those, a line of those posts, let's say mimicking, I don't know, grass or boulders or something like this with characteristic spacing. If you make an array of those and you let the robot run into that array over and over and over and record where it goes, surprisingly, you find a multi-peaked probability distribution to find that robot post-collision with the array. And that multi-peak distribution reminds a physicist of a so-called diffraction pattern, diffraction being a characteristic feature of wavy phenomena. So this snake robot or limbless robot basically kind of is localized in space. If you blurred your eyes, it might look like a kind of wiggly particle, but it interacts with the environment like a wave, and you get sort of wave-like phenomena. And if I squeeze down the spacing between those posts, the robot spontaneously, emergently responds by scattering more broadly. You essentially end up with kind of like a robotic uncertainty principle, which I would not have predicted a priori, and so was a big surprise to us. So the fact that we can see kind of like wavy quantum mimicking phenomena in very simple robots, to me, interacting with environments and being allowed to interact with complex or seemingly complex environments is a testament to just how far we can go in discovering cool phenomena, which we could eventually use. That's one surprise. And the biggest surprise also is that when we went to test that in an animal to see if we could see this effect in a living system, we indeed were able to see it. And the mechanism by which a real snake essentially diffracts from an array of posts is actually reliant on its soft body properties. So that brings us back to soft robotics. And in fact, adding to that, we were then able to take those principles by which we believe the snake functions, meaning how it activates its musculature and how its passive body properties conspire with its active body properties. And we were able to basically make a new kind of limbless robot that can solve complex arrays of posts, meaning that it can go from A to B without any brain power or control at all. You just put it in the lattice in a regular array of posts, and it pops out the other side without us having to program it to do that. And that's all a function of the kind of mixture of soft and hard and active and passive elements in the body. And so I would never have predicted that. And so those are sort of that's one arc of surprise for me.
So I'm curious to ask you in that case, because we speak about we can't evolve everything that reduces the fitness. For example, we know that these animals are designed a certain environment to adapt. And for example, why we don't have fitness as human. And that's a question, how do you see the fitness of these animals? And do you believe that through robotics we can push the limits to certain application? Not necessarily we have to look what evolution had already. So how do you see the fitness in the design, the morphology of the body of the animal to adapt to environment? And do you think the fitness in robotics can be surpass what we have already in evolution for a certain commutation of an expression?
Evolution by selection, you know, we tend to not talk so much about design, but indeed certain organisms have certain adaptations which confer certain advantages in certain environments, and they are, you know, selected naturally and to improve indeed fitness, or can improve fitness. You know, those adaptations. Okay, so let's talk about locomotion, which is something I know. You know, we talk about adaptations for sand swimming. Let's say something we spend a lot of time on, or adaptations for movement across the surface of sand. And often the problem is we'd like to know whether organisms have evolved certain features like long bodies or short limbs or interesting pointy shaped heads. And we can speculate on that, but typically, at least in pterodynamic environments like sand and leaf litter and tree bark and grass and these sorts of things, we haven't had kind of models, environmental interaction models, theoretical models of the organism, incorporating important aspects of morphology and control to test those hypotheses, right? I said, well, I hypothesize that the sandfish's wedge-shaped snout allows it to control its descent into a granular medium, in addition to not allowing sand to get into its jaw. It has a pronounced overbite. How do I test that? Well, if I don't have a model of the environment, or I don't have a model of how the soft body of the lizard couples to the sand, then it's hard to put some meat to that statement. The nice thing about robots, and like I say, like I mentioned, since I'm a physicist, we call what we're doing robophysics. It's sort of the physical modeling aspect. We don't have an environmental model. We can take a robot, and we can design, now with 3D printing, it's relatively easy, heads of different shapes and motors which can control that to test hypotheses about that function, that presumed adaptation. So that's kind of the physics approach, the biology/physics with the physics of living systems, or what I'm calling living systems physics approach. And then the hope is that can couple into work that engineers are doing to help them better design devices that can actually credibly move in those environments. So my point is that indeed we can speculate on adaptation and increases of fitness via various bits of morphology and control. But until we have models to test this stuff, and then to vary parameters, oh, what if the sandfish had a 30-degree wedge head or a 45-degree? We don't know. And we're starting in certain areas, at least pterodynamically, to get those. Folks have been doing this very well in aquatic and aerodynamic and hydrodynamic environments, to the point that people can design quite good fish-like robots and starting even kind of more flapping-like robots to test such hypotheses. And we're starting to get there with pterodynamic environments too. And hopefully that'll inspire some nice robots.
Yeah. But I'm just ask you again about the damage here, because we speak about how it happened in evolution, if this damage happening in the brain or the body, how they can also adapt to each other. And also some cases already we know people they can feel the pain through their bodies, and that's like disorder. So how do you see that in the studies you do, if there is damage happening, how they can adapt to that? Yeah.
Oh, you're saying, did you just say damage as in like robot damage? Oh, that's a great question. One actually I've started to think about a little bit, not in any deep, serious way, but we have been studying now for some number of years how collections of ants, fire ants, which are a big pest in the southern US, United States, how these ants can excavate collectively, thousands and thousands of ants, which dig their way into the ground by creation of little tunnels, which are very narrow tunnels, meaning they're basically about 1.5 ant widths can pass in a tunnel, maybe 2 when they're first starting. And so if you watch that, the ants are moving, they're squeezing by each other and grinding by each other. And our attempts to make robot models to kind of get at aspects of such kind of confined traffic have really revealed just how important it is to not only allow the robots to flow past each other, but to prevent damage. And we don't know what the best kind of robot is, soft robot that can squiggle and wiggle around in a complex environment while performing its task, but not suffering tremendous damage when it gets jammed and crowded and pushed and squeezed. And so we can look to organisms like how the fire ants are managing to do that and presumably not be broken by the time they're done squeezing past their neighbors. How, for example, the other famous example from Bob Full's group is how cockroaches can squeeze through tiny gaps. Here is just an enormous range of interesting problems, I think, that roboticists can contribute to. So I don't have any smart answers at this point, but clearly soft components are very important in such systems.
I guess that's you in that case. Do you think that we can design a robot that can never damage? And do you believe there's, I don't know if you have any examples of evolution that you see that they can resist damages or have tough properties?
Oh yeah, I think that's almost the definition of living systems, right? Is that they manage to mitigate in their environments. They manage to mitigate damage and loss of components very well. You know, I think that, like I say, the fire ants is a nice example from our own work where these things are just going back and forth and grabbing particles and grinding against the particles and grinding against their neighbors, and yet you can watch the same ant perform hundreds and hundreds of trips back and forth, and those tiny little limbs remain intact, and the tiny little antennae remain intact. And our robots, a few trips in a very crowded environment, a gripper will break or a sensor will break off, and or the body will tear apart. And so the question is, how do you avoid that? And I think that so long as the robots aren't interacting with their environment, meaning via contact, we're really obsessed with sort of contact interactions. So long as that's happening, is keep your robots apart, then you don't have to worry about it. But in confined environments, so I think that organisms that live in those environments have a host of properties which I can't even speculate on yet, which help prevent, mitigate, and repair damage. I wish I could give you anything smart to say about the secrets for that, but I'm convinced that that's an important component of future, particularly robots that have to move in really cluttered, complex environments. Contact.
I think we have a few questions left. I'm curious about maybe what could be something for you. Do you think we can add more for designing embodied intelligence? Which direction or focus we have to give more? Which direction you believe that we have to investigate more?
Well, I don't know direction. I think that there are interesting principles to be learned via systematic laboratory study of robots or self-propelling devices with interesting environments, with complex environments. I think that is something which, you know, it's great designing a device and designing a new material, a new sensor, and demonstrating that it does something is great. I think, though, that really pushing to test these things systematically on self-propelling devices is in the laboratory, systematically and repeatedly, and not simply look to optimize a particular design via some machine learning, I think is a valuable component to add to the toolkit of folks working in soft robotics. Look for, in fact, there's lots of interesting phenomena that one can learn from in how soft robots fail in certain environments. An example from my own group, which I still think is really interesting, is we wanted to understand how little hatchling sea turtles, which are, you know, born in eggs on in a nest and clamber out of the nest and run past their nest mates and have to avoid predators like ghost crabs and raccoons and gulls and run down to the ocean and then swim for the rest of their lives. But in that running, they use soft and hard appendages, their flippers, to manipulate all sorts of complex materials, including hard sand, soft sand, beachy grass. And they do it pretty well. They can move at multiple body lengths a second. So how are they doing that? Well, we studied them in the field, and we developed a hypothesis about how they were doing it, that they were somehow using a soft kind of passively flexing wrist to locally insert into soft medium and basically offload the control and the manipulation of the granular material to kind of the mechanical properties. So to test that, we built a kind of robo-physical model. We call it FlipperBot, I think, at the time. And what we discovered is that for the most part, it didn't move very well. And so we started investigating why didn't it move very well, but not because we want to necessarily improve how well it moved, but we were curious as to what parameters in the problem were important, allowed to move. And by that systematic study, we discovered actually cool new phenomena in how the robot, and we then later hypothesized the turtle, how they can control basically when the material yields and doesn't yield, and how they can then, that lead to kind of an ability to keep themselves off the ground. But we weren't necessarily making a turtle robot to optimize to go from A to B. We were studying the kind of principles of interaction of that robot with the environment. And by doing that, we were able to discover some of those principles, which can lead to better robots. So that's the kind of philosophy and approach that I think would be a valuable addition to the soft robotics toolkit and community.
Very wonderful. Yeah. Yeah. So I'm curious to ask you, if there's any kind of, maybe when you try to look for creature, there's something you don't know how we can design that. Or for example, there's a trade-off which you can't really design that, engineer that design. And there's unavoidable trade-off that you didn't understand how this creature really evolved in that way. I don't know if you have any kind of thought like that.
Oh, well, I would say that most living systems, my baseline, and I am happy to be proven wrong, my baseline is that we can't engineer most of what living systems can do. Meaning we can't make a robot that has the functionality of a nematode worm at this point, right? Something with only, quote unquote, only 302 neurons. And why can't we do that? And to me, that's a very interesting question. Why don't we have, we could certainly make cars which move faster than any living system, right? And jet planes which move faster than any flying system, and speedboats which move faster than any swimming system. But we can't kind of generate devices which have the capability and flexibility of seemingly lowly little worms. And why is that? And so, I don't know. I think what you're asking about is design trade-offs. I think that we're still very primitive in even what our robots can do in environments that we might find interesting for soft robots. Let me put it back that way. I think we're good at certain things, but not yet good at the things that the soft little wiggly critters are so good at.
That's very interesting. And it's fine. I don't know if we make a question. Do you believe that we have to understand how they behave, for example, or how this kind of mystery is happening in this creature? Or it doesn't necessarily important to that we go for this level and understand the tiny details?
Well, again, it's really a question of what understanding means, right? What does it mean to understand? Do I need to if I want to understand, again, how a nematode works, meaning how it wiggles through a piece of rotting fruit, do I need a full model of the rheology of the rotting fruit? Do I need to know the connectome of the nematode? Do I need to know the biophysical properties of its muscle? Do I need to know what do I need to understand, right? And that, I think, is an interesting question. And that's what the engineer designer can say, oh, actually, what I need to understand is maybe how it changes its shape as a function of time. Okay, well, I don't necessarily want to mimic what a nematode is doing, but if a nematode is swimming in a gel, and that gel is kind of stiff or soft, do I need to understand the detailed physics of how that gel interacts with the body? or do I need to just simply understand kind of roughly how little, if I were to drag little plates through that gel, how those experience forces. And if I were able to understand those, then maybe I could understand how to sum up a bunch of those little plates to form the shape of a nematode to then optimize how well it was. So it's really a question of what one needs to understand for the challenge at hand. Right?
Yeah.
I don't know, again, one doesn't know until one is interested in a particular system. I would say.
Yeah, since it was end a few questions. First one, I'm curious if you have any doubt in sometimes in research when you try to ask a right question or problems. Yeah, I don't know how do you deal with doubt. I don't know if you have doubt. Yeah.
Yeah, doubt. Of course, research is the thing I think which I love about research, but which I think terrifies certain students or people, is that you typically don't know the answer, right? You don't, not only do you not know the answer to the problem you're trying to study, is to why does the centipede have this many legs? Why does a sandfish have a head shaped like this? You don't even know if it's an interesting question to ask. Okay, who cares if the sandfish has a head like this? And so one has doubt at all. That's a theme today at every level, right? Oh, I'm doubting. Did I pick the right screw to use? Did I write the right sentence? Did I ask the right scientific question? Did I do the calculation right? Did I do my error analysis right? It's all about doubt. And in science, you're basically, and in anything I think that requires sort of an answer at the end of the day, you eventually check things in enough different ways to help mitigate the doubt on specific topics. And then I guess if your peers and colleagues find what you're doing interesting, then you might say, well, that alleviates some of my doubt about whether it's interesting. But at the end of the day, it's only what you have in your heart. It tells you if you find it interesting. And so it's constant doubt, but you learn to live with the uncertainty and doubt. And that's actually what being able to do science is all about, in my opinion.
Right.
And it's a hard thing to learn, and not everybody wants to do that, right? Because it's tremendous uncertainty at all times. Now, the nice thing is that if you end up getting a job as a professor or a researcher of some kind, you have some buffer against uncertainty, right? I have a nice job which pays me to teach students physics classes, and also I can write and pays me to also write grants to try to fund the students in my laboratory, and so it's a great job. And so I'm buffered in some way against some doubt, but there's still always doubt. Will I get the grant? Will I publish the paper? Will my students succeed? Will my students be happy? All these things.
Yeah, wonderful. Yeah. So I don't know if you have any crazy ideas, or maybe when you try to sit and think what you want to do, maybe in the future. I don't know what kind of thoughts, imagination for your research and lab, and I don't know what kind of thoughts maybe.
Yeah, I have all sorts of crazy thoughts and ideas, and some most I don't want to share. But I will say the craziest thing to me is that when I was a kid, I loved lizards and snakes and the living world. And then but I somehow decided, well, that's not serious stuff. I should go and learn physics and relativity, and that's serious business, deep questions of the universe. And I've been able to come back to my childhood love and integrate it with my love of physics. And to me, that's the craziest thing and I'm actually paid to do this, one, and can get money to do this, two, and that some of even this crazy stuff that we are interested in, like a little lizard, how a little lizard swims in sand, turns out to have practical application for example, the same scheme that lets us understand how a lizard swims in sand is starting to tell us things about how wheels should be best designed for moving in loose material, like regolith, extraterrestrial soil. So to me, that is a crazy, from a little wiggling lizard in sand, I one day imagined that a robotic rover that we helped work on understanding control principles for NASA might one day be exploring, the lunar poles or moons of planets. That to me is a kind of amusing story.
Great. Yeah, interesting. I don't know if you have any book maybe you read last year that was very interesting, maybe in the field or outside the field. I would like to share any book you read.
Yeah, no, I tend to enjoy reading these days histories of science and engineering, and in fact, I just have been reading or read, and in fact, the author is a good friend of mine, a book on a Nobel Prize winning physicist who you might not have heard of, a man named Philip Anderson. Well, Anderson was a professor at Princeton, but he was at AT&T Labs for years. And he won a Nobel Prize in so-called solid state physics, and is essentially the person who really kind of helped bring about the field of condensed matter physics, of which soft matter physics is now a thriving sub-discipline, and which ideas from soft matter physics of jamming and glassiness and bifurcation, phase transitions, and can be brought to bear in soft robotics, I believe. I recently read the biography of Anderson called Mind Over Matter, and I would recommend that to folks. People may know of Anderson outside of physics because of a piece he wrote in Science magazine in the 70s called More is Different, which was a very influential piece for many physicists, and basically saying there's been a kind of a funny argument in physics as to what is fundamental, and what is fundamental to study, and what is fundamental to fund. And is the only thing fundamental that which is smaller than what I'm presently studying, or at a higher energy or something? And Anderson knows that no, you can find fundamental at every scale of organization and every type of science, and no one discipline or question is more fundamental than another. And in fact, he didn't say it in his piece, but this kind of idea of emergence, an emergent phenomena, where basically if I have a bunch of elements that operate under some rules, when they come together, the rules that ensemble operates at may be completely different, are often completely different than the rules the individuals operate at. And that we call emergent phenomena, and it's a whole source of cool phenomena. And so that biography I highly recommend, More is Different, by Andrew Zangwill, about Philip Anderson. A good history of condensed matter physics, solid state physics, and science and engineering, that interaction more broadly. And to me, it's inspirational because I think that soft robotics is a great place where engineers, control theorists, and scientists, physicists, biologists, chemists, mathematicians can interact incredibly.
Interesting. So much for sharing that. Thank you. So I don't know if you have any, maybe because you shared the advice list episode last year. So I don't know if you have maybe advices or something you gained through this year, because it was pretty challenging. But I don't know what could be advices or something, maybe it's changing your way of thinking, or I don't know if you have any something you would like to share that.
I don't have any smart advice to say. I wish I could give advice. Just try to find what you love to do, and try to find a good mentor. Those were bits of advice that were given to me, and the older I get, the truer they are.
You shared that last episode, and it was very interesting advice and very important. So thank you. Daniel, I don't know if you have any final words like to say before closing. Do you have any
No,
final words?
I want to thank you for this wonderful service you're doing, and clearly it's a passion for you. And so I think it's a wonderful thing. And hopefully there are students out there who are hearing this and are become interested and inspired, and feel free to contact me.
Thanks so much, Alex. I think it was very inspiring. And thank you once again. It's an honor to have you again. Wonderful. Thank you.
Thank you so much.